So there are lattice sites on which we have electrons. And the question that was posed was, what are the relative ordering of spins of the electrons on successive lattice sites? So is it like this or is it like that? So that was the question we were trying to understand. But there are a class of, and there are materials like this, and I'll just come to cite one in a few minutes. But there are other magnets, and in fact, this study of magnetism, or in particular, the proposal of the Hubbard model, on which we have spent some time, came in the context of these three materials. If you open the periodic table, these are all 3D transition metal elements, and the solids, the elemental solids of these three, they are ferromagnetic metals. These are metals. These are metals in the sense that electrons, I mean, these solids are bonded through metallic bonding, and that metallic bonding is due to both 3D and 4s electrons of these atoms. And again, these are these 3D electrons which are responsible for magnetism in these materials. Okay, so how to understand that? Because in the kind of picture we were drawing, the electrons that were responsible for magnetism, magnetic moment, the wave functions, we did not specify them very clearly, but the electrons were supposed to be sort of the largely localized picture. Okay, so we'll come to that. We'll try to understand these in detail. So let us start with these two phase diagrams. So these are called phase diagrams. I'm not sure you can read it very clearly, but what I have written here is ferromagnet. So let us try to look at these phase diagrams more closely, and then we'll get to the actual discussion. So what is being drawn in this picture is the phase diagram. Now, what is a phase diagram? You have a system or a model, and you have certain parameters that you can vary. In experiments, you can vary some external conditions, maybe. And you ask, what is the sort of state of the system for different combinations of those parameters? And what is drawn in the first picture is the mean field phase diagram of the Hubbard model, Hubbard model on a three-dimensional cubic lattice. So I have a Hubbard model, the Hamiltonian for which I wrote down earlier. So that is the Hamiltonian. This Hamiltonian is now, we are talking of a 3D cubic lattice, which is just an extension of the 2D square lattice in 3 dimensions. And what is being plotted along this axis is U over T. And on this axis is N, the filling. The filling is number of electrons divided by the number of lattice sites that I have in the system. So, so this is the N equal to 1, half filling, 0, and 2, that's the maximum you can have. So this is a phase diagram of a one-band Hubbard model, mean field treatment on the NU plane. U, of course, means U over T, because T sets the sort of scale of energy. And what you find here is that as you move away from half filling, or right at the half filling, and at fillings that are not very different from half filling, you have this antiferromagnetic region. So this whole region, the system is antiferromagnetic. And you see there is a complete symmetry around the n equal to 1 line. Whatever you have on the right, you have exactly the same thing on the left, mirror symmetry. That's because of particle hole symmetry of this Hamiltonian. So let's not get into that detail. So these are paramagnetic regions, and these are the ferromagnetic. So these two lobes that you see here, these are ferromagnetic regions. So mean field treatment of Hubbard model at some filling, roughly about quarter filling, and large enough U, you have ferromagnetic regions. So what this means is that for these combinations of N and U, paramagnetic state has the lowest energy. For these combinations, antiferromagnetic state has the lower energy. And for these regions, the ferromagnetic state has the lowest energy. So that's what the sort of mean field treatment tells you. Okay. So one should be happy that, some region in the phase space of this Hubbard model, you do have a ferromagnetic ground state, which could possibly explain the ferromagnetism in these transition metal systems. But then you remember that this is this is a mean field treatment. And you probably told me last time that you haven't done a great deal of, phase transitions. You haven't really studied it. But it turns out that when you are doing a mean field treatment of anything, what you are neglecting is basically fluctuations. Okay. Just to give you a flavor of what a mean field treatment is, one example that we discussed was last time when we said that we discussed Weiss molecular field treatment of the very phenomenological treatment of the ferromagnetic system. So what we said is that each moment experiences a molecular field which is proportional to the magnetization of the system. So each moment is experiencing the same field which is proportional to some kind of average of the moment due to all other fields. So that's an example of a mean field treatment. It's a mean field that each of these moments experience. Any fluctuations from one spatial location to another is neglected. So this is a very crude sort of explanation of the mean field treatment. But the point is that what mean field treatment does is that it neglects fluctuations. And if you neglect fluctuations, what you will have is you will tend to have more order in the system. That's the crux of the matter. If you neglect fluctuations, you have more order. So if you go beyond mean field and you bring in fluctuations in your treatment, in other words, if you do more accurate, more exact treatment of the model and don't go for a mean field solution, on very general terms, what you expect is that your ordered regions should shrink. Okay. So if the mean field treatment gives you this much of ferromagnetic region, and remember there's a paramagnetic region here, which means it's a disordered state. So if you go beyond mean field, you expect this region to get smaller, not bigger. So, so if it gets smaller as you go beyond mean field, then what this tells you is that maybe the Hubbard model on a cubic lattice does have a ferromagnetic ground state, but that's probably at very large values of U and over a tiny range of filling and so on. So it's not the kind of, it's not a satisfactory explanation for the kind of robust ferromagnetism you see in these systems. So what do I mean by a robust ferromagnetism? These are pretty large TCs. The Curie temperature of iron, for example, the TC is, I think, something like this, over 1000 Kelvin. Okay, so it is pretty large. So that state at very large values of U over a tiny range of filling seems rather fragile to describe ferromagnetism in these materials. And by the way, in case you did not know, these are the only 3 elemental solids that show ferromagnetism. There are no other elemental ferromagnets. So all other ferromagnets are compounds. These are the only 3 materials that become ferromagnetic as elemental solids. Okay. So some initial success with the Hubbard model, particularly this mean field phase diagram, raised the hope that maybe we would be able to explain ferromagnetism in these materials through the simple model of one band Hubbard model, okay, on a hypercubic lattice. But then you realize that these ferromagnetism in these materials are rather robust, and the kind of picture you get when you go beyond mean field is probably not a satisfactory situation. So yeah, so something more is required. This hope was also, I mean, this initial success actually, let me tell the other part of the story here. This initial success of the Hubbard model, the success was particularly in terms of explaining the antiferromagnetic kinetic exchange and the Mott transition. So that brings me to the second diagram here. So what is drawn here is a phase diagram of a real material. Okay, this is not a model. If you can read this compound, let me write it more in a bigger font here. This is the compound written here. So the parent compound is La2CuO4, lanthanum cuprate. Have you ever heard of this compound or this class of compounds? Anyone?
Sir, I have heard of YBCO.
YBCO in which context?
In superconductivity.
Yes. So this class of compounds, when you dope them with something, so this was the first compound in which, first compound of this class in which superconductivity was discovered. That was mid 1980s, 86, I think. So lanthanum cuprate, which is a well-known insulating material, when this was doped with strontium beyond a certain doping, below a certain temperature, it became superconductor. And that temperature, I forget the exact number, but that temperature was tens of Kelvin. I mean, 30 Kelvin, 40 Kelvin, something of that order. I forget the exact number. And that was a big surprise. Because all the known superconductors had Curie the transition temperatures that were very small, below 10 Kelvin for sure. So this was these class of materials started this field of what is now called high TC superconductors. So the point was that it is not just that these materials had high TCs, and then people discovered other cuprates, which now I think the highest would be about 150 to 100 Kelvin of TC, which are way higher than all the other superconductors known before them. And it turns out that it's not that just that they have much higher conducting transition temperatures. It's also that the mechanism of superconductivity in these materials is very different and still unexplained as compared to the conventional superconductors, which are explained in terms of what is called the BCS theory. So forget about the mechanism of superconductivity. So this is the phase diagram. Okay. So one is plotting X here, and the parent material when X is equal to 0 here, it's an antiferromagnet. It's an antiferromagnet, and if you do a sort of conventional band structure calculation, you will find that that produces a metal which is completely wrong, because the material is known to be an insulator. It's an antiferromagnetic insulator. So this is an example of a Mott insulator. I'm not distinguishing here between what is a Mott insulator and what is a charge transfer insulator. Let's not, but if you ever come across this term, just note that there is slight difference between these two. But what I'm trying to say here is that these are insulators, not because of electron valence electron count. These are not band insulators, but these are insulators because of electron correlation effects. And I'm terming it as a Mott insulator. So it's a Mott insulator and an antiferromagnetic. It's the kind of system that we discussed in terms of the Hubbard model. Okay, half filled. In fact, the parent compound happens to be well described by a half-filled Hubbard model. There is a kinetic. There is an antiferromagnetic exchange in the spirit that we discussed, except that the real crystal structure is more complicated, and what is at play is not really the direct kinetic exchange between two the kinetic exchange between two successive magnetic sites, but rather a super exchange, which we did not discuss. But apart from those details, the point is that these are insulators because of electron correlation effects, which also gives rise to an antiferromagnetic order. And when you increase X beyond a certain value, below a certain temperature, so this is temperature axis, this is X axis, the amount of doping, you get a superconducting state. So it was also hoped that a whole host of electron correlation effects, in particular antiferromagnetism. So what was the hope? The hope is that, or the hope was that, a single band, that is one orbital per site, Hubbard model, can describe a whole host of correlated phenomena like antiferromagnetism, Mott insulating state, or the Mott transition, ferromagnetism, band ferromagnetism, I mean, and several other things which we have not discussed. General, just let me mention one, heavy fermion systems, and high temperature superconductivity. In this class of materials, because it was realized that the superconductivity, well, in any material, superconductivity is a consequence of electron interactions of some sort. So it was believed that this correlation effects gives rise to the superconductivity in these materials, and one could possibly explain this using a simple one-band Hubbard model. What is one really trying to understand? One is trying to get a qualitative understanding of, so the target for us is right now are these. We are not getting into these. So our target is these ferromagnetic metals. And what one is trying to do is to get a simple model which gives us some sort of physical insight into the origin of ferromagnetism in these materials as a consequence of electron correlations. Because describing ferromagnetism in these materials theoretically by other means is not difficult at all. Again, just to give you the perspective, the standard method that is used these days for calculating band structure of real materials is based on a theory called density functional theory. Let's not worry about what this theory is. What it does is basically it solves for the Hamiltonian, which is the full Hamiltonian of the system. So I have the electronic energy, I have the electron-electron interactions. So I'm writing everything in atomic units. And then you have the ion-ion term, I mean the nucleus-nucleus term, okay, which is of course treated classically. So capital R's are the coordinates of the nuclei, and the ith one has charge Zi, and small r's are the coordinates of the electron. So this is the full Hamiltonian, and the problem here is this term, the electron-electron interaction term, and such problems cannot be solved exactly, but there are ways you can solve this, and that's the method that is used for calculating band structure of materials, including electron interaction effects at some level. So, so these kind of theories for calculating band structure produces the ferromagnetic states in these materials perfectly well. In fact, what they do is, for example, if I take iron, the magnetic moment per iron turns out to be, so it's something like this, 2.1 mu V or something. The point is that it's a fraction. But in these kind of lattice models where you have integral number of electrons on each site, the moment can never be a fraction. Okay, the moment per site will be an integer times mu V. So that's a challenge that these models face, that how can you describe ferromagnetism in these materials where the moment, for example, on iron is something like 2.1 mu V per atom. For nickel, for cobalt, it turns out to be something like 1.6 mu V per atom. For nickel, it turns out to be something like 0.8 mu V per atom, and so on. So these moments, fractional moments, cannot be explained by the kind of discussions on the models we had earlier. So that's a challenge that one faces, and one tries to, explain this based on a simple Hubbard kind of model. So that's the idea. Okay, so that's what we'll get into now, and we'll discuss what is called the Stoner theory of ferromagnetism for band magnets. And this will be in contrast to the magnetism we have been discussing so far. So in order to discuss this, let us try to understand what we are, or let us first clarify what we are trying to understand, what we call a magnetic order. So what we still think in terms of a lattice system. Okay, it's not a continuum we are talking about. We are still thinking in terms of a lattice system. So we mark the lattice sites by I, and what we are saying is that we have a certain imbalance of the occupation of up and down spin states at different sites, and we say that this, the expectation value of Lz is so this is how Sz, expectation value of Sz, is defined, and we have a certain imbalance in the number of up and down spin electrons. So these are expectation values of up and down spin electrons at the site I. So at each site I, this is non-zero, and then there is a pattern of those, non-zero values, which determines what kind of order I have. Is it a ferromagnet? Is it an antiferromagnet? Or is it a more general spin density wave state, which I told you I'll explain. So today I'll explain that. So what happens is that, let me just remind you, what has happened is that when this is not zero, we are in a broken symmetry state. And what is a broken symmetry state? So one thing which I explained earlier is that we have broken the continuous spin rotational symmetry of the Hamiltonian. But actually, we have broken some other symmetries. So what other symmetry have we broken? Manojit, can you tell us?
No, sir.
Aman, any answer? What other symmetry we might have broken?
The translational.
Yes, I mean, we are not, see, we are not talking about the continuous translational symmetry at all anymore. That's sort of accepted, that whenever you are on a lattice, you have broken the continuous translational symmetry of free space. Now, sitting on this lattice, what are the symmetries? So my Hamiltonian is defined on a lattice, okay? So therefore, not worrying about breaking of the continuous translational symmetry. What other symmetries have we broken? Have you learned about discrete symmetries in your quantum mechanics?
Yes, sir. Parity.
So have we broken any discrete symmetries here?
Parity is broken, sir.
Parity is broken. Why is that? Parity is not broken actually. What is broken is the time reversal symmetry. Whenever you have Sz is or any component of S not equal to 0. So what happens under time inversion? What happens to S? How does S change under time reversal?
It flips.
Sorry?
It flips.
Harshit, could you repeat that?
Hello? Yeah, the
Ha,
spin
Harshit.
flips.
Spin flip. So S goes to minus S. So Sz will go to minus Sz. So you have broken the Hamiltonian is completely spin. I mean it doesn't change under time reversal, but the state does because each side has a definite Sz. Okay, so that time reversal symmetry is broken, and depending on whether you are ferromagnet or anti. If you are on an anti-ferromagnet, then even the discrete translational symmetry of the lattice is also broken, because if you are on a ferromagnet, all sides are equivalent. They have the same Sz. But if you are on an anti-ferromagnet, and we are assuming simple two-lattice antiferromagnetic, two sublattice antiferromagnetic state. So this is up, this is down, this is down, this is down, this is down, this is up, and so on. So if I translate this point to this, I don't recover the same situation. So I have to translate this by this much. Whereas the lattice translation is this much. So the discrete lattice translation symmetry is broken in an antiferromagnetic state. Only some subsets of all the possible lattice translations are symmetry operations in an antiferromagnet. Okay, so these are some things you should keep in mind. It's not completely broken, but only a subset of the symmetry operations of the original lattice are now symmetry operations of the antiferromagnetic system. Okay, so that's the situation. So what happens in a, so this is true of any magnetic system. So what happens in a ferromagnet? What is the kind of order that we have in the ferromagnet? In a ferromagnet, we define ferromagnet as ferromagnets as A9 sigma. That's a ferromagnet. So Si Z. Simple. Now, what about antiferromagnets? In antiferromagnets, you define two sublattices. So we are assuming a bipartite lattice, which can be neatly divided into A and B sublattices, so that each A sublattice site has B as its neighbor and vice versa. And let's say there are majority up spins on A sublattice and majority down spins on the B sublattice. So we can write that situation as the following. M is a number that is greater than 0. And so therefore, so if the occupation is n by 2, you have exactly balanced system, equal number of up and down spin electrons on each side. But now there is an imbalance. On A sublattice sites, you have more up spins than down spins. So here, A down spin is here. So more up spins than down spins. And on the B sublattice side, there are more down spins than up spins by an amount m. So m is the sublattice magnetization. So this is how you define an antiferromagnetic, or how you can represent an antiferromagnetic ordered system. But let us now write this in the following way. Okay, so we write this as, or we try to combine the ferro and antiferro descriptions in a common language, and we write it this way. So let us see what happens if we, how we can, using this, how we can describe an antiferromagnet. So let us think of a 2D square lattice and take Q to be the vector. Pi over A, pi over A. Then it's quite arbitrary, but let us take this side, this A sublattice side, as the origin. Okay, so then in order to reach another A sublattice side, I have to take an even number of steps in terms of nearest neighbor steps. Okay, so this or this, that, and so on. So therefore, for the site I to be on A sublattice, I or Ri has to be a vector of the form in one A x plus into y, where this is an even number. So now let us see what we get here. So if I do it for upspin, I get n plus 2. For upspin, this is plus m e to the I pi over a dotted with a vector this. Now what will I get here? This a's will cancel. I'll, apart from factor of pi, I'll get n1 plus n2. So this is but n1 plus n2 is even when I is on A sublattice. So this will give me 1. So I'll get this. Now it's straightforward to see that if I happens to be on a B sublattice, you have to take an odd number of steps. So n1 plus n2 will be odd. So you will get a minus sign. So you'll get this for the upspins. For the downspins, it will get reversed because this eta will now be minus 1. So the important point to notice is that this vector, so if I define expectation values of up and down spin electrons in this manner and choose Q to be this, then I get the antiferromagnetic order on, in this case, I showed you the example of a 2D square lattice, but on any generic, any hypercubic lattice, this is what we'll get. So you have to define Q, and in fact, the A's are not written because that sets the scale of your distance on the lattice. So this Q is equal to pi pi in 2D, or Q equal to, on a hypercubic lattice, this is called the ordering vector. So pi pi is the antiferromagnetic order on a 2D square lattice. Pi 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 would be the antiferromagnetic order, one type of antiferromagnetic order on a 3D cubic lattice. And if you take Q equal to 0, 0, you'll get the same thing for all lattice sites, because you know, if it is 0, 0, you'll just get e to the 0, so everything will be the same. So therefore, you get a ferromagnetic order. So the ferromagnetic ordering vector is 0, 0 or 0, 0, 0, whatever. So from here, you get the idea of the ordering vector. Now, who tells you that Q has to be either 0, 0 or pi pi? Q can be any general vector, right? And in fact, it can be. So the general case is what you call the spin density wave. So you define occupation numbers this way, and you can derive the corresponding expression for S, that is Sz, which will be a function, which will be an expression defined by this Q, the ordering vector, and you can have any general Q. So that state or these states in general are called spin density wave states because there is a wave of spin density with a wave number q. Ferromagnetic states and antiferromagnetic states are special cases in which q has these values 0, 0 or pi pi. You can even have states where the q is not commensurate with the periodicity of the lattice. If the ordering vector of the magnetic state happens to be incommensurate with the crystal structure, it does happen for materials. These are incommensurate magnetic states. These are incommensurate spin density wave states. So you get the general idea of a spin density wave. The term is self-explanatory. You have a density of spin on each lattice site, and there is a wave of those densities. That wave may be commensurate with the lattice. The most trivial cases or most straightforward cases, the simplest cases where you have exactly the same periodicity of the lattice, which is the ferromagnetic case. The next case you can have is this sort of two sublattice antiferromagnetic state where the periodicity in each direction becomes double the, that is, you have to go twice the distance of the lattice to get the same spin density. So that's the two sublattice antiferromagnetic state, but you can have a very general Q, which can even be incommensurate with the lattice that you have. Okay. Any questions at this point? If not, let's now look at the mean field treatment of this Hubbard model and see if we can understand ferromagnetism from it. Okay, so let me write the Hubbard Hamiltonian once more. So the problem is this term. As I told you before, this part is simple. This is the usual tight binding model. We know we can solve it. We can find the band energies given the lattice on which it is defined. But the second term is the problematic one. It involves interactions, and such problems cannot be solved exactly. I mean, yeah. They are not easily solved. So here what we'll do is what is called the mean field treatment. Of a certain kind. I mean, there is various ways you can do a mean field decomposition of this term. Sometimes what you do is you sort of assume the existence of a certain ordered state, for example, it could be an antiferromagnetic state, and you break the interaction term, the 4 fermion operator, in a manner that is sort of, that represents that ordered state, and then you try to solve the Hamiltonian, find its energy, and etc. So here what we'll do is we'll write this term in the following way. So we haven't done anything. We have just added and subtracted the same things from both these. So this is the expectation value. So these are just numbers. Expectation value of the upspin number operator, and similarly for the downspin number operator. So we'll treat this as a sort of a single object and write this in the following way. So this and that, then this and that, and then this and this and this and that. Okay, so what do we get here? In I up operator times this, similarly I'll get in down operator times this expectation value. Okay, what remains from here is product of expectation values, same quantity, and the same quantity here. So two come with minus signs, one with plus signs. So finally, I'll get a product of the expectation values with a minus sign. And then I have this term. Now, what is this? This is the number operator of upspin minus the expectation value of number operator of upspin. So which is the fluctuation about mean of the number of upspin electrons. Similarly, this is the fluctuation in the number of downspin electrons around the mean value. And these, so the product is a product of two fluctuation terms, two fluctuations. And if the fluctuations are small, the product of two fluctuations would be even smaller, so we will neglect that. So that's the sort of mean field approximation, that the fluctuations are small. I told you a little while earlier that mean field theories underestimate fluctuations. And so here is an example. So we'll neglect that term. So we are left with this. So the last term is just a number. It doesn't involve any operators, but these two involve operators. See what we have achieved. We have written the two number operator, that is 4 fermion term, into product of, into two terms with one operator and one expectation value. So the interaction term has now been decoupled. So there are no 4 fermion terms anymore. Okay. Now it turns out that, let me see which expression we want to work with. All right. All right. We'll leave it at that. And then we'll go to this situation. So this is the mean field treatment. This is just a constant. So we neglect that for the moment. So now we want to write the energy of this system in the mean field picture that we just wrote earlier. So how would I write that? So I can write this as so I have written the band part in K space. All right. And then this is the mean field decoupling of this. We also now assume that there is an external magnetic field. Let's say. Which generates a certain spin density at each site. And so, which leads to, Ni up. See, I'm assuming a ferromagnetic order. So I'm doing my treatment assuming a ferromagnetic order. Okay, it sort of doesn't come out of the calculation, right? So using this decoupling scheme, the mean field decoupling scheme that we wrote here, what is the energy of the system? So what is the magnetization? The magnetization is M, or yeah, it would be half of N up minus N down, expectation of N up minus expectation of N down. So that is M. M is the magnetization. So the energy of the system when the magnetization is M is the sum over band energies, sum over the energies of the occupied bands, plus the interaction energy, plus the interaction of the moment with the external field. So whether I have to check this factor of 2, but doesn't matter. So what are we writing here? These are the band energies. Occupation of the upspin bands up to the chemical potential of the upspin bands. Occupation of the downspin bands up to the chemical potential of the downspin electrons. And the dispersions are, and the densities of states. So B epsilon are the densities of states. Right. So what we are trying to get at is what is the change in energy when you have a magnetization in the system, and we'll compare that to the energy of the system when there is no magnetization. So I'll just delete this part. The interaction term is still there. The density is the number of up and down spin electrons are the same at each side, which is n by 2 in case of m equal to 0. So that's that term. So now we do some tricks. So what we do is mu naught is the chemical potential when there is no magnetization. Okay, so this is the expression for EM. This is the expression for E0. And I have sort of decided to break these integrals into two parts, from here to here and from mu naught to mu sigma. So when you take the difference, the integrals from -infinity to mu naught would cancel, and you'll be left with only this part. So if you evaluate this part, you'll be left with this. And then minus squared. So this u, not u squared, this is un squared by 4. So that will cancel out. You are left only with the m part, and then this. Yeah, so this 2 should not be there. If the magnetic field is weak, the bands are not disturbed very much compared to the h equal to m equal to 0 state. So then in these integrals, and see, these integrals are just over the range mu naught to the chemical potential in absence of field and magnetization to the new chemical potential when we have applied the field. So the change is, so this is over a small region, and if the change is not large, we can simply replace these by the density of states at the Fermi energy of the original system, the non-magnetic situation. So in that case, what we do is this. Yeah, there's something more that we have to do before that. Okay. So in up, the number of upspin electrons. And similarly, we'll have in down. So you subtract, so these parts cancel out, and you have and now in these integrals, I replace d epsilon by d epsilon f. So I pull that out, and then this when I pull d epsilon out, it just becomes integral d epsilon from mu naught to mu up, and similarly mu up, mu naught to mu down. So you can easily do that, and you end up with this. Mu naught from the two integrals. So the mu naught will cancel. You have mu up minus mu down. So there's a factor of 2 somewhere, or let me just write this as d epsilon. Delta mu is mu up minus mu down. Okay, I don't know why I have a factor of 2 here. Maybe that's how I defined it. Yeah, let's define it with a factor of 2, then we'll see. So then delta mu would be half of mu up minus mu down. And then by definition, m is half of ni minus down. So we have these two relations. Okay. So now we'll get back to this delta EM. So can I erase this lower part? So I'll erase this part. So let me write these things here. All right, so we come back to this. So first, we do look at the band part. So not this part, we are looking at this part. Now, clearly, you can integrate those two. You'll get something, I mean, epsilon squared by 2, you put the limits and so on. And then if you manipulate, you will eventually get this to be equal to So this algebra you can easily fill out. You have all the relations there. This is what you will get. So look at this here. So delta, one second. N up minus N down is defined in terms of delta mu. And M is in terms of Ni minus N down. So if you use these two, you can write M is equal to d epsilon f times delta mu, right? Which is obvious. So now I can, so in other words, I can write delta mu as m squared over d epsilon f squared. So I can put that in here. So what I'll get is m squared by epsilon f. Okay, so that's the band part. Now we have these two as well. So what I'm doing is now I'm minimizing this energy, okay, with respect to m. So we're trying to find out which value of m would minimize this energy. So we put this equal to 0. So that you can easily work out and you will get okay, so that's the magnetization. That's the value of the magnetization, which minimizes your energy. So once we have the magnetization, we can calculate susceptibility. Okay, and susceptibility, as we said, is this. So if you, again, if you, that's, you know, it's just linear in age, so that's rather trivial. So what you have is, oh, by the way, M is not the magnetization. M is, this is the value of M which minimizes this. Now remember, M is just a number. It's the number of, it's the difference between up and down spin electron numbers. So in order for us to convert these to magnetization, so the magnetization has to be G mu B times M. And then you calculate del M del H. Now the expression is still linear in H, so the derivative is rather trivial. And so that is chi, and you will get this as this is written as chi Pauli divided by 1 minus d epsilon f. So this brings out several things that I mentioned earlier. So what would happen if u was 0? If u was to be 0, the denominator would just be 1, and the susceptibility of the system would be just this part. Okay. Remember, while talking about various types of magnetic systems, I mentioned something called Pauli paramagnets, which have temperature independent susceptibility. So these are that. This is just that. This is just that susceptibility, which is proportional to the density of states of the electrons at the Fermi energy. There is no temperature dependence. There is no temperature dependence because there are no sort of moments in the system. There is equal number of up and down spin electron density. Electrons live in bands, and these are delocalized states. The up and down spin electrons have exactly the same spatial character. So at each point, or if you think in terms of lattice, at each lattice site, the density of up and down spin electrons are same in such systems. The susceptibility is temperature independent and is just proportional to the density of states at the Fermi energy. There's nothing else, in fact. Mu b g, g is of course 2, let's say, and it's just the density of states at the Fermi energy. But when you introduce interaction in the system, when the electrons interact through this u, you have this denominator, 1 minus u density of states at the Fermi energy. So that basically, what does it do? Okay, it's something less than 1, let's say. So it enhances susceptibility. That is, the electrons now start responding to magnetic fields to a greater extent. I also mentioned that one can think of a diverging susceptibility as some sort of instability in the system. So now suppose you start with u equal to 0, you start thinking about the u equal to 0 system, and then you start increasing u. When it reaches, when u becomes when u equal to 0, of course, you have a paramagnetic system. No moments, no magnetization. Then you start increasing u, and when u reaches this critical value, 1 over d epsilon f, the denominator becomes 0. So you have a diverging susceptibility. What happens then? Well, what happens is there is an instability in the system, and beyond this u, the system becomes ferromagnetic. That's the ferromagnetic instability, just calculated. So you need a critical u. Once you are beyond that critical u, the paramagnetic state is not the most favorable state anymore. The system undergoes a phase transition and it becomes ferromagnetic. Let us look at the situation in a different way. I have a certain u, and I'm asking what is the sort of density of states at the Fermi energy. Now, if the density of states at the Fermi energy becomes large enough so that u d epsilon f is equal to 1, then I have an instability in the system. Okay, it would prefer to be a ferromagnet. In fact, that is exactly the sort of situation. I'll now erase this part. So let me draw two band structures. Okay, so I'm plotting schematically. Okay, now if I draw the the density of states corresponding to these two systems, which one would tend to have a higher density of states at any energy? So as you see, what is different between these two situations are the bandwidth. This has a larger bandwidth, this has a smaller bandwidth. So the question is, which of these would tend to have a larger density of states? If I plot density of states over this energy range, so over this energy range here, I'm plotting density of states, d epsilon, over this density of this energy range, I'm plotting d epsilon. So which one would tend to have higher values? The one on the left or the right?
The one
Left.
on the right. No, the right
Someone
one.
said left, someone said right. Aman, what is your argument?
Sir, the slope is higher on the left hand side. It means in narrow K, you have large span of E.
No. What I wanted to say is that the span of K is the same. So the total number of K points are the same in the two cases. But what is different is that in one case, the energy range is larger. The other case, the energy range is smaller.
Yeah, then the right one.
Then the right one. So if you have the same number of states over a smaller energy range, of course, you have to have larger density of states. And then extreme case would be when you have a completely flat band. Then the density of states would, sort of be a delta function. So now if you have such sharp density of states or peaks in density of states near the Fermi energy or at the Fermi energy, then this theory tells you that that system would be unstable and it would prefer to go to a ferromagnetic state, would sort of develop moments which would lower its energy. In fact, that's how you explain ferromagnetism through this. So this condition is called the Stoner condition. So this criterion is called the Stoner criterion, and the band ferromagnets are actually sort of understood within this picture. And in fact, you can sort of go beyond the immediate, materials that you know are ferromagnets: iron, cobalt, and nickel. A very interesting case is palladium, and another interesting case is this material, cobalt carbide, CO2C, not COC, CO2C. Palladium is a metal, of course, and it happens to have a large density of states at the Fermi energy. I'll try to show you a sort of plot of density of states for palladium. So it's not ferromagnet. Bulk palladium is not ferromagnet, but because of the fact that the density of states is large near the Fermi energy, this denominator is pretty close to 1. It's not a 1. Sorry, it's pretty close to 0. It's small. So it's not 1. So therefore, there is an enhancement in the susceptibility. It doesn't quite become a ferromagnet, but the chi is enhanced because of this large density of states. So these are called, this phenomenon is called exchange enhancement of the susceptibility. The susceptibility is enhanced because of this effect, and as a result, even small perturbation can cause huge response in the system. In fact, what happens is that if you put a single magnetic impurity in palladium, because of the fact, let's say iron, because of the fact that it has a large chi, the response is large, and a large part of the system actually get magnetized because it has a large susceptibility. And CO2C is not even fully understood, but there are several reasons for that. I won't go into the details. One of the reasons is that it's very difficult to do experiments on clean bulk samples. But it is believed, and there are reasons to believe that this may actually be a ferromagnet in the ground state, but it is not known experimentally for reasons I just said, that it is a ferromagnet because of this exchange enhancement, because of this effect. Another example which is discussed in Fazekas's book is, I think, if I remember correctly, it's this alloy, Zn, Zr2, I can check it. Here the interesting thing is that none of these elements are actually magnetic by themselves. So pure zinc or pure zirconium, none of these are magnetic. It's the other way around. Let's see, Zr, Zn2. Zr, Zn2, that's the alloy. But this is a ferromagnet. This is a ferromagnet because of, again, this the large density of states near the Fermi energy. So the Stoner criterion makes it unstable to ferromagnetism. Okay, so so basically that's it about band ferromagnetism. Let me now see if I can find a picture that I can show you. Just give me a minute. Let me see if I can find it.